So let's have a look. I just handed that one problem back, so why don't we take a look at that one? That's actually a pretty good 3D review, right? So what we do here is we find the coordinates of points A, B, and C. Then we want a force vector from B to C. So you take, to get RB to C, you take RC minus RB. You get the position vector from B to C. You take the square root of sum of the squares and find its magnitude. You divide through and get the unit vector. And then you scale the unit vector up by the amount of the force. So you get down to the unit vector there, the negative 0.496, the 0.211, and the 0.842. You scale it up by 5,200, and you get a force vector. Okay. Good to go from B to C. Okay. Then you get vectors. Now what we're going to do here, we're going to check both the axial force, which would be a projection, which is a dot product, and also a moment. So I want to get unit and position vectors between A and B. So I decided to go from A to B with my vector. So I took RB minus RA. I got from A to B is 0.9, negative 4.2, and negative 1.6. Took the square root of sum of the squares and divided through and got unit vectors both from A to B and from B to A. Okay. So I'm getting set up to do both a projection and a moment. So we're good with that? Good to go? Then I start working through this stuff. What I do first, I decided to find the axial force from A to B. So that's compression. I can see that when I just look at the sketch, because that blue force vector, this one here, is pulling. It's going to take B and push it towards A. So I guess that force is pushing B towards A. That's going to be compression. So I want my unit vector to be from B to A. That way I'll get a positive answer. Now, had I used the unit vector from A to B, I just would have got a negative 3,038. I could kind of see what was happening though, so I set up my position vector, my unit vector from B to A, because that's how that component of force is directed. So I went ahead and did that. I did a dot product with the unit vector to get the compression 3,038, realizing then that the compression and shear are perpendicular to one another and that they make up components of the total vector. I used the theorem of Pythagoras and backed into the shear, which is 4,220 newtons. So we good with that? I could have done the whole vector business with that, but given the question, I didn't need to go through the whole vector process on that. So I just did a theorem of Pythagoras kind of quick and got to the answer that I wanted, which was a magnitude. Okay. All right, so that gets me the compression and the shear. Now, I did point out in class that even though you were given a spec or a allowable limit for tension, you didn't need to worry about that because there is no tension in that shaft. It's all compression. So with axial forces, it's all one or the other, and in this case, it's compression, so I didn't need to worry about the tension on that. Okay. All right. Now the next thing here is a moment vector. Now to do that, I want RAB. Okay, I want the full vector from A to B because the length of the moment arm affects the magnitude of the moment. So it's RAB crossed with FBC. Okay, now the vector goes from the point about which you take moments, which would be A, to where the force is applied. And to remember that, I think of using a wrench. What I do with a wrench is I put the head of the wrench on a bolt, which is what I'm going to take the moments about, and then I push on the wrench with my hand, which is where I'm applying the force. So the wrench goes from the bolt to where I apply the force. Okay? The position vector should do the same thing. It's a full position vector too, because the length of that vector matters. So I want a full vector there that reflects the true length of the line. So we're good with that? Any questions on that bit? Now the last little bit of this was to find the how much force I could apply. Now there's of course many different ways to approach this, as you know there often are when you're doing different kinds of problems. The way I approached it was, first thing I wanted to do was identify which situation would cause the shaft to fail first. So the way I'm thinking about that is I have like what we call a turnbuckle in this cable. So this is a cable and I've got a turnbuckle in here that allows me to keep turning it and getting it tighter and tighter and tighter. Which mode will that shaft fail in first? Now the key thing on this is if you tighten up the turnbuckle and increase the 5,200 Newton force slowly and just ratchet it up, it's a linear relationship. It's just proportional. If you double the force in the cable, you will double the compression, you'll double the shear, and you'll double the moment. If you triple the force in the cable, you'll triple the compression, the shear, and the moment. Okay, so it's all proportional. So what I wanted to do first is to identify the critical load first. Okay, so what I want to do then is look at the allowable loads and then look at how much I've got. So for compression, my allowable is 12,000. And currently, when I have 5,200 newtons, I've got 3,039 newtons applied. That gets me a pretty big ratio. That's 3.95. Okay? I can almost increase that load by four times, is what that's telling me, and still stay within the allowable limit. Okay? Now the shear is is not, I don't have near as much margin, but let's look at the shear. The shear maximum I think is 6,000. And currently when I've got 5,200 newtons in the cable, I'm at 4,220. So I can divide those out and I still have a fair amount of allowance in there. The moment is the one that's the most critical. Okay, so what I've got for the moment is I've got 22,000 allowable, and currently for 5,200 newtons I've got 19,343 is what I came up with. Now that's getting a little closer. That's at 1.13. Okay. So what that's telling me is that the moment is the critical thing here that will cause the shaft to fail, that will take it over its allowable limit. So all I have to do now is take the 5,200 newtons and multiply it by 1.13, and that will get me up to the load that would cause the shaft to fail on account of the moment about A. So 5,914 newtons would be the value that would cause the shaft to fail. Got any questions on that last little bit there? Okay. Okay. All right. So that's that one. Now let's have a look at this test review that I gave you, or preview might be a better word for it. I don't know. Okay, so that little process there that I just went through, the idea there was first to identify how failure would occur, and that's all based on the fact it's all proportional. If you double the load, you double everything, the compression, the shear, and the moment. So that whole deal then was just based on working with that and just kind of backing into what the force would be. That was the idea there. Okay. All right. All right, let's have a look at this preview, you might say, and we could just have a look and we'll see if there's questions and whatnot on this one. So I have the list of things that could be on the test. You know, be sure that you're not just doing the test review and saying you know everything. Be sure to look through the list and be sure you can do those types of problems. The things for sure that you're going to want to be able to do is the stuff with position vectors. You want to be able to do a dot product and realize that it's how you find tension and compression. And you want to be able to do a cross product and realize that's how you find 3D moments. So I know for sure I'll put stuff like that on this midterm because those are important things that you know. Okay. So start off by studying by being sure you can do those things. Now the way you're sure you can do those things is you take a problem, you write it down, and then you do it. And then you look at the solution after you do it. Okay. And you're sure that you can do these processes. Okay. That's how you're sure too. You simulate what you're going to have to do on the test. Okay. Make sure you can do it. That way when you're on the test, you can do it. Okay. So that's how I would approach that. All right, and then there's other topics here, that I went over. So are there questions on any of the topics to start? Okay. And then there's the vocabulary too. Okay. And, take a little bit of time, know the vocabulary. I could ask you to find compression, and you're not going to look on that formula sheet and find compression, right? That's not on there, but you have to know that you find compression by doing a dot product, right? So you have to take the words and understand, given the words, how to find what you need to find, okay? You want to look at your blue formula sheet so you know what format it's in and where things are and what they look like. Okay. So remember that the cross product and dot product formulas are right on there, but they're in the lower left-hand corner. Have a look. That sort of thing. You have to use a non-programmable calculator, which is basically, they call it the fundamentals of engineering exam type calculator. That's getting to be a requirement for certain type of exams. So be sure you've got one, or I'll bring some, but all the same, be sure you can use it. Because again, I've said it a number of times, I'll say it again, you don't want to figure out how to use a calculator in the middle of a midterm. That's not a good time to figure out how the syntax on a calculator works. You figure that out before, okay? All right. Now the last thing, so we good with the vocabulary and all that? Doing all right? Okay. Now the other thing I want to point out then, if we're good with all that, is the format that I use sometimes. Now, there's a problem with giving a test in 3D that I have is that they take so dang long to crunch all the numbers. Okay, so I've tried to develop some methods to cut down on that time so that, to cut down on the time it takes you to do it. And here's some different ways that I've come up with. One way I've done is I've had people find vectors in the first part of the test. Okay, so what you'll notice here on these example problems, the third one down, and these might have different numbers on them, but the third one down has a force vector that you're supposed to find. And then the fourth one, which I think is on the back side, has some position vectors to find. Okay? Then after you've found the force vectors and the position vectors, the next thing to do, further on down in the test, so after you found the force vector on the third one and the position vector on the fourth one, the next thing to do is to use those vectors to do some things. All right, and when I grade that, this test was set up in that fashion, okay? So what I would do when I was grading this thing is I would look at the answers that you got for the vectors. I would kind of divide the test into a couple of piles as I was working through it. The people who got the vectors correctly and those who did not. And the people who got it incorrectly, I had a spreadsheet I could plug the stuff into and see, what their answers should have been given their answers that they got on problems 3 and 4. That was one way to do it, okay? You with me there? That way I can have you use the same vectors over and over after you found them. And if you made a mistake on them, I could just account for that mistake and grade the next problem separately, okay? Now, that's one way to do it, and I might do that. Now, if I do that, you got to read the question and not go through all the time of redoing the vector every time, okay? You've already got it, okay? You with me there? So pay attention to how I set it up and how I write it up, because if I do it that way, you don't want to waste time recalculating vectors that you've already found, okay? Now, that's one way I can do it. Now, another way I can do it is just to give you a sheet of vectors. And this is another approach. So just be aware of that I might do that. And if I do, I might have you find some vectors on the first page or two just to be sure that you can do it. After that, I'll give you some vectors. And then you can start to just use the vectors that I give you and figure out the rest of the problems using those vectors. And I'm trying to see if what I can find here to explain what I mean by that. Let's see. All right, so here's what I'm talking about, and unfortunately the graphics, I do this stuff in AutoCAD, so the graphics don't work the best. It's not the easiest to read, I know, I'm sorry, but what we've got is I have, on the very last page, I have a graph that shows where the vectors are. So on the very last page, I have a graph that shows where the vectors are. Then I have a table here that's basically an Excel spreadsheet. And what I've got is I've got the vector. Let's try this. File, print. Sorry, I'm just having some computer problems. The screen's kind of small, and when I touch it, I'm hitting zoom features. I'm kind of zooming in and out. It's a little frustrating here, so let's get this put somewhere else where I can get to it. There we go. Okay. Yeah, I think it'll get at the bottom of the stack then, and I'll be able to find it. All right, and I know that's, unfortunately, I can't overcome that when I pull something out of AutoCAD, but what I have here is I have a spreadsheet set up where I have the vector, and I just call it out, whatever the vector is, and then I have the position vector, and then I have the unit vector. Okay, and then I might have vector AB, and then for the position vector, what I'll have is a column for I, a column for J, and a column for K, and then I'll have the same thing for the unit vector. So what I'll have is a variety of information about a given vector that you can then use to pull off and use as you wish on the test, okay? So the idea here is if you use these vectors on the back, you don't have to calculate this stuff every time.
So you say something like, what's the moment of the unit vector A with respect to the position vector?
Yeah, that's kind of the idea. So what I might have here for RAB, and I just want to pull out something that has some meaning here. Let's say I got -4, -7, and 2, and then I'll have the unit vector, -0.482, and then -0.843, and then 0.241. So that's what you'll have on the spreadsheet. So then what I might ask is find FAB, and I'll give you a graph, and I'll show you that FAB equals 600. Well, then you got to know that you take that, and what do you multiply that by to find FAB?
Your unit vector?
Yeah, so you got to know you got to pull that off, right?
Okay.
And then I might have multiple questions where, you know, you've got that vector there, and then you have another one. And let's say we've got, you know, whatever, R, B, C. And I'm just trying to find unit vectors where I don't have to do all the calculations on them, but let's say that that is 3, 4, 5. And then I would give you the unit vector for that as well. So that would what? Be the square root of 9, excuse me, 9 plus 16 plus 25. So that would be the square root of 50. Put that in memory. Okay. So 0.424, I'm sorry, I'm just kind of figuring out what these would be. 0.424. 0.566, 0.707. Okay. So what I might have you do first is to find FAB, and then I might ask you, all right, let's find the moment of, so then that might be question number 1. And then question number 2 might be find the moment of FAB about point C, okay? So what you would then do is, what would you do? You would use the FAB that you already found, the 600 times the unit vector, and then what would you use for your moment arm? What's that? Yeah, this one, right? Okay. So, you know, I'm kind of stumbling through the computer usage here because I'm having some problems with my computer, but all the same, you know, that's basically what we're doing here, okay? So I'm giving you all the vectors. You've got to know which ones to use, which vectors to pull out and use, and you have to know what form to use them in, unit vector, position vector, whatever, okay? So if I do it that way, I'll give you a separate sheet that has all the vectors on it. Okay. Y'all okay with that? All right. And I would give you, and I just wouldn't ask you, I just wouldn't put letters on there. I'd have a sketch and I'd show you, you know, where the things are and all that sort of thing. Okay, I'd have an axis system similar to what I've got on this sketch here, okay, which I've kind of covered up with all this stuff, but anyway, okay. So just be aware that I might do that, and if I do, use the information that I give you. If I give you vectors, or if I have you find them previously, you don't need to find them over and over again. That's not, it's wasting time. And all I'm trying to do is to save time. That's all I'm trying to do. Okay? So any questions on what I'm saying there? All right. All right, so that's, and you know, that's one way I might do it. Now, okay, on this particular test, the way I did it was I had you find the vectors first, and that was problems 3 and 4, and then I had you use them later. So you just had to find them once, and then you could use them. All right, so number 5 there was find the compression in AC caused by FAB. So what's the operation you would do to find the compression in AC? So dot, right? Okay. And you've got the dot, you know, you have to know you have to apply the dot product. You've got the, you've already found the vectors, so you just go ahead and do the dot, okay? Number 6 was to find a moment. Find the moment of FAB about point C, okay? That's a cross, right? So you do a cross product. So are we good with that? Okay.
It's about C, so you have to do CA because you want C to be at the base of your
Yeah, you have to do the vector.
To RCA.
Yes, from C to A, yes. And that vector is kind of called out here, and yeah, that's, oh, Lord. There we go. RCA, right there. Okay. Okay, so we good on those? Dot and across? And for sure you're going to see that stuff, so get ready for it, okay? Just be sure you can do it. Okay, here's find a resultant. Express your answer as a vector. So you're going to find FAB. That's going to be done with position vectors. You're going to find the position of B, find the position of A, find the position vector, find the magnitude, divide it out, and scale it up by 2,000. And then you'll find a vector for F1. Okay? And then you just add the two together to get the resultant. Okay? So there's a resultant problem with some new vectors. Okay? So you would have to find those. So any questions on that one? Doing that?
Number one.
Yeah, okay, let's go back to the beginning then, okay? Number one. Okay, so what are we going to do on number one? Yeah, right, that's about the cosine, so cosine 117, right? That's the I. So to get the unit vector, you take cosine 117 for the I, cosine 31 for the J, cosine 76 for the K, right? And then you'd scale it all up by 3,600 newtons, something like that. And then you just work your way through that. Okay. Now the next one is what? That's a double projection, right? Should we go through that one? Can you see that one? Okay. Now the fact that that's a double projection, you can see that because you are not given one angle to any of the axes. So if you see two angles that go from the force vector to an axis, you're going to have to apply two trig functions to project it onto the different axes. So here's how we're going to approach that. We've got 4,700, and that's what you'll multiply through. Okay. Now let's start with the y-axis. This will be the j component. To get from here up to the y-axis, you're going to go cosine 29 to get up to the xy plane, and then cosine 17, and that'll be the j component. So 4,700 times cosine 29 gets you into the xy plane, and then if you take that, you project it onto the y-axis, it'll be times cosine 17. Because what you have here are a couple of right angles. Those are right triangles. Okay?
So whenever it's a projection, I can always assume that it's a right triangle.
Yeah, if you're given the, well, let's see, you can assume this. Well, there is a reason why you can assume it, and the reason you can assume it is this line is parallel to that axis. And so that way, that creates the right angle right here. And then this line is parallel to the x-axis, and that creates the second right angle. So that's the reason, why those assumptions can be made, because of those dashed lines that are kind of showing, they're like dimension lines, is what they're like. Okay. All right. Now the I component there, you're going to have what? Cosine 29 to get up to the xy plane. And now you got to get onto the x-axis. Well, you're going to have to come around that way to get to the x-axis, right? So 90 is the difference between the x and y axes. 90 minus 17 is 73. There we go. That will be the I component. And what I'm doing there, I'm taking the 90-degree angle between the x and y axes. I've already used up 17, so what's left over is 73. Okay. Okay. Now the last one is up to the z-axis. 90 degrees is the angle between the z-axis and any angle in the xy plane. We're going to go that 90 and then 29 degrees more below that. So that'll be plus, and that'll be cosine 29 plus 90. So 119 degrees. And that'll be the K. So there's that vector right there. So do we have any questions on that? It's a double projection there. Okay. Okay. Then we've got the one with the position vectors, and there's basically what you're working through there is to go from A to C, you take RC minus RA, square root of sum of the squares gets you the magnitude, divide through by the magnitude, you get the unit vector. Oh, I'm sorry, that's the one after. Here we go. For the force vector, what you would do is find the position of the coordinate of A and the coordinate of B. Why don't you write down the coordinate of A and B there just for practice there. This one, although it's just different than what you've got. This is different. Oh, no, it's just the one up above. Oh, I see. Okay, I've got 3 and 4 on page 1. Okay. So how about coordinates of A and coordinate of B? So we got 7, -4, 9, and 0, 0, 10. Okay, we good on that? Okay, we good, all right? So we want to be able to read those coordinates, okay? So from A to B, you're going to take B minus A, get the vector, take the square root of sum of the squares, get the magnitude, divide through, and scale it up by 8400. That's the steps. Okay, you're sure to have to do something like that on Wednesday. Okay. Okay. Okay, we've got those coordinates there. Again, you should be able to read the coordinates, so that's important that you can do that. So there's a second problem. That just involves position vectors and unit vectors. Once you find these, you just take the negatives to get to that. You're just multiplying through by -1 to get to these other vectors.
So when you're saying find the vectors just in FOIL, generalized, like you're just taking it from both.
Well,
Do you want us to show both ways?
no, if you just can do one and take the negative of it, that's, I know enough about it, and I assume you do too, but that's good. I don't need you to run through it all over again. Okay. I just setting that up so you could use the vectors in all different ways in the test down the line. That's why I did that. Okay. All right. All right, and then we've got dot product here, and then a cross product, you know, so you should be able to apply those. We get on the resultant problem there. Yeah, question there.
Number one, the other number one, that would find the resultant of
Uh-huh.
FAB.
Mm-hmm.
Can you just elaborate? Why is it just a simple addition on that one of the two vectors?
All right, so on this problem, you just got to find the vectors first. So you've got AB, which is you got A and you got B, so you just do the regular vector business on that. Now you do have the angles for the F1, I'm calling it. Now see, even though that isn't the origin, the same rules apply. You've got basically a coordinate system that's translated up there to point A, so you can use those angles to generate the vector, okay? And now to find a resultant, what you're doing, the only thing you can add together arithmetically with vectors is like components. So you break the vectors up into I, J, and K components, and you just add up the like components. I mean, that's, because those are the only things you can add.
You find your unit vector from A to B, and then you
Yeah.
multiply the magnitude.
Yeah, to find AB, you would do that. But a resultant is just a sum. It's the result of applying both vectors, essentially. And the only way you can add them is to add like components together. Okay. All right.
How about this weird cable one?
Okay, yeah, the word cable one's a 2D one. So we want to find the force in each cable. Now that's equilibrium, right? 2D equilibrium?
Yeah, are you using like tangent to find those angles?
Sure, yeah. Yeah, there's one angle to find. You got to do an arctan of that. 5 to 4, so it's 51.34 degrees.
Oh, yeah, there you go.
Right there. And then it's a sum of Fy and a sum of Fx. To solve that, I went sum of Fy first because there's only one y unknown. Once I run that equation, I get FBC. I can go sum of Fx and solve for AB. Okay. All right. So we doing all right with that? Okay, now another thing on this test that I will typically do, I try, you know, I never perfectly succeed at this, but what I try and do is make, let's say 70% of the test is basic knowledge, another 15 or so percent is a little bit more advanced, and then the last 15 more advanced yet, okay? So there might be some short little things on there that might have a little higher difficulty on them, but keep your eye on the points, okay? I might have a difficult problem that's worth only 5 points because I want to kind of see who could really use this stuff creatively. Don't spend a half hour doing a 5-point problem. That's not don't do that. Get the easy points first. The ones where there's lots of points assigned, do that first, and then come back. And don't worry about it if you can't do some of that or whatever. I never quite know when I make these things up. Sometimes they might be challenging, sometimes they're not. I mean, I never really know when I make them up, but there might be some smaller, shorter things that might have a higher degree of difficulty, but don't worry about that. Save that for last, and don't get the easy points first. Do the problems that have a lot of points first. Use your time wisely. Okay. So be aware of that you might see something like that on there as well. Okay. So we good with that? We got any questions on that? Okay. Yes.
So when we're just finding theta of like in the homework we turned in, we're finding just the angle of the resultant force.
Mm-hmm.
And it's just, we just take, if it's like a negative 67.7 degrees, we just look at it as where the force is pointing.
Yeah, right. It's visual,
It's not, yeah, so it's not mathematical, like you don't have to do stuff.
Yeah, if you're doing a 2D problem and finding the angle of a force, and you have the components, the formula is arctan of, sum of Fy over sum of Fx. And arctan is also known as tangent to the -1. They're the same thing. You're going to run that number, and you're going to get an answer out of that. And by default, your calculator will give you the answers that are in quadrants 1 and 4, I think. And so you have to watch out, because let's say you get the tangent of -1 and it comes out to be -3. That could be -3 over 1, or it could be -1, or excuse me, it should be +3 over -1. And your calculator does not know the difference between these two things. Apparently I don't either, but let's see if I can write that down. There we go.
Except for it'll tell you one is undefined if you try and.
No, it won't, no, I don't think it will. I mean,
Oh, wait, no.
those are two correct answers to the same problem. See, those two vectors are doing these two things, okay? And your calculator does not know the difference because it does the division first, and then it forgets about what went into the division. So even though you get an answer, and I don't offhand know what the tangent of our arctan.
71.5 degrees.
I'm sorry?
71.5.
71.5. Okay, so it'll give you negative 71.5, but what that might be is this one here. Okay, and so to find out, you just look at how the signs lay out, you know.
Do you think the orientation of our force could tell, like if we have a negative force or a positive?
Well, yeah, but
You can
although
just
when
see
you're,
that it's going
yeah,
down.
you can look at it and tell. I mean, that's usually how I do it. And quite often, might have an answer where you actually draw it, because I want to know, you know, which way is it going. Yeah, so, okay. So be aware of that. That comes up. Other questions? Good. All right. Oh, we'll take a little break here till 4. We'll start up again, and we'll start on some new stuff, I think. Now, if you